Okay, thank you for attending. I feel like I've been at OCP. This is probably like my 7th or 8th OCP in a row. So great to be here again. Great to see lots of familiar faces, and thanks for attending our talk. My name's Danny Moore. I'm the Director of Product Marketing and Product Management at Rambus. I've been working in CXL, the CXL space specifically, since CXL's inception in 2019. Before that, I was working in PCIe switching and different interconnects. And today we're going to give a presentation describing some of our forward thinking around composable pieces such as memory scalability. In particular, all of the presenters before us have kind of touched on memory as a critical piece for generative AI specifically, and we're just going to expand on that a little bit more. Taeksang, are you ready? Can you just give yourself a quick intro and then?
Yeah,
perfect.
Yeah, hello. I'm Taeksang Song, and Technical Director and Memory Architect at Rambus. And I'm working on the emerging memory solution, including the CXL memory expander and pooling and the other memory types for all the AI and ML system. Before joining Rambus, I worked on the SK Hynix and the Micron, and then read some kind of the emerging memory subsystem architect.
Okay, perfect. Thanks. Okay, there's a lot of aspects that are going into machine learning and artificial intelligence. The big one that I want to reiterate, or one of the big ones that I really want to reiterate with the team, with the people here, is memory. I don't know if I could say it enough. It's very, very critical. It's probably one of the most critical subsystems within a cluster, an AI ML cluster. And what are the impacts to the memory subsystem as we kind of progress into this new phase of generative AI and the large language models specifically? These are a couple quotes that were pulled out of a microprocessor report written in 1996. Almost 30 years ago. You might recognize some of the names there. Bill Daly is very prominent. I think he leads NVIDIA research right now. And even then, he was articulating in very plain language that processor speed, which is what we used to call compute, processor speed is simply outstripping memory, right? These are kind of the foundations of the people who started to describe the memory wall very, very early on. And one of my favorite quotes, which I always like to include, I don't think it could have been summarized more eloquently than Dick cites himself in that same a magazine, not a blog, magazine. It's the memory, stupid. Because they recognized even then that the processor speeds were simply outpacing what the memory could do. And they found, but their processors, the majority of time, Pepe touched on it, are simply waiting for memory. So what is this kind of Cambrian explosion in generative AI doing, and what is its relevance to the memory subsystem specifically? So I've kind of highlighted some main points here, but overall, if I could just impress upon you one simple takeaway is that, the compute, the intensity, the sizes, everything is getting bigger. And fortunately or unfortunately, depending on your perspective, the demand on the memory subsystem is also getting larger, just to try to keep up. And the memory subsystem in itself is struggling, as it did 30 years ago, as it was so eloquently pointed out by some of the seminal computer architects back then, that the memory subsystem is continuing to struggle to try to keep up. So the models themselves, obviously we all know the models are getting larger. We've all seen the graphs. They continue to expand in size. LLMs are no different. Again, they continue to get larger and larger. But also with LLMs, there's an aspect that we also need to consider. And that is that, when we think about traditional AI, we think about an inference. We one pass through the cluster, we get a result. With generative AI, the final result isn't fully calculated until the previous result has been calculated. So if you ever go on ChatGPT and you ask it a question or you ask it to write you a poem, you'll notice that it's literally typing out the words. And that's actually what's happening in the memory subsystem as well, right? The poem isn't completed until the last word, the last token is shared, and that last token isn't calculated until the previous one was shared. And so, the model sizes are getting larger, but then as the Gen AI is creating content, generating content, it is also continually to expand the memory subsystem requirement. Many people may be familiar, if you've been running a lot of LLMs, you get an out-of-memory error, and that can simply happen if you're running too many tokens, for example, or too large a batch size on an LLM, then you can just simply run out of memory. You might not run out of it right away, but eventually you run to a place where you're running out of it. The training data sets, as mentioned earlier, the training data sets are enormous. They're not getting smaller, they're getting larger. And as the training clusters themselves continue to get larger, they're thirsting for larger and larger data sets as they build bigger and bigger models. The inference piece is one of the pieces that I mentioned previously, right? Now the K-value cache needs to be constantly updated. So the memory subsystem itself, it's not a static demand of just model weights, for example. Now with generative AI, the memory subsystem demand is actually dynamic as well. Latency, obviously very, very important. And with respect to generative AI, once again, like what I was saying is it doesn't inference one time. It's looping through the transformer. It's looping through it over and over and over and over and over again until finally it gives you the last result. Before it gives you that last result, you've got 99% of it. Whereas in inference, we generally think of it as providing a single result at a single moment in time. The hardware, at Hot Chips this summer, Bill Daly from NVIDIA again was mentioning, they're training some of these contemporary LLMs right now are training on tens of thousands of GPUs. And I heard someone comment even just yesterday that, that was last year. The hardware requirements they're not getting smaller right now. They're getting larger and larger. And we've got a lot of smart people are working on ways that we can make the LLMs consume less and less memory. But at every moment where an optimization is made, the pure thirst for more and more larger models continues to consume any additional space generated by any of those efficiencies. And then efficiencies, to comment on that, right now a lot of the inferencing, for example, that is being run in the data center based on DLRMs or what you're using when you're interacting with different apps. It's somewhat been optimized, right? But with LLMs right now, we're in this kind of like hyper-growth phase where people are prioritizing performance and they're prioritizing accuracy over some of those optimizations. So we don't quite get that same kind of level of efficiency that we might get in traditional AI. So once again, just as a primary takeaway, I just want to reiterate that the demand from the generative AI is just building additional complexity and demand on the memory subsystem. So I'm going to pass it over to Tech Sang here, and he's going to talk about some future-looking architectures and reasoning around. Our title didn't work out well. Okay. Thanks, Tech Sang.
Thank you, Danny. So Danny explained the memory requirement for generative AI very well. So today I would like to share some kind of one of the compelling memory configuration for generative AI and training. So title covered some kind of content. So NVIDIA everyone knows that the data should be placed to the compute resource as close as possible to minimize the power consumption and to minimize the access latency. So for AI and ML system, then question is that which data should be placed to closer to where? So one of the interesting kind of the trend we can look at these days is GPU can directly manage all the data movement or the computation directly with less interaction with the CPU. So traditionally, CPU initiate all the RDMA kind of the communication for distributed computing in HPC workload. And CPU is known that it can execute some kind of the data pre-processing and the extraction or data transformation to the different size or the different layout and cleaning the data very well. But if you look at these days trend, for example, the GPU to GPU or the GPU to NIC integration have some opportunity that the GPU-initiated RDMA instead of the CPU-initiated RDMA. So by using this technique with the MV SHMEM or the ROC SHMEM kind of the libraries, then it allows the actually GPU thread to allow the NIC access by using some kind of the command queue, thereby no CPU interaction. Same technique can be applied for the kind of the streamlined data movement from the network attached to the storage to the GPU memory side. So by doing this one, we can reduce the latency by removing any kind of the CPU interaction. And in terms of the data pre-processing, the GPU vendors provide some kind of solution like the DALI and Rapid to accelerate the entire end-to-end workflow can be covered by GPU itself. And the computation, including all the nonlinear, dense matrix, and sparsity operation, can be done by the GPU's SIMT or the tensor or sparsity cores. So it is very obvious that all the memory architecture should be optimized to feed the data to the GPU efficiently. So if you look at the ML and the AI server, there are two main memory types, HBM connected to the GPU and main memory connected to the CPU. Recently, Samsung announced the kind of the bufferless HBM concept, which can be directly integrated on top of GPU core instead of the 2.5D configuration to bring the data to the GPU closer further and further. Then question is that what about main memory? Main memory also should be optimized to provide the data with a higher capacity and higher bandwidth capability. And considering the collective communication, then the kind of the effortless or the improved data sharing also essential. So question here is that how we can re-architect main memory subsystem to feed the data to the GPU efficiently for the generative AI kind of the application. And the font is a little bit weird, but sorry. So one of the solution we are considering is that directly attach the main memory pool to GPU cluster. So this slide shows the left side figure shows the traditional the AI system. So there are multiple GPUs, and GPU can exchange data directly through the CPU without any CPU interaction. But when CPU accesses the main memory data, then they have to pass through all the PCI switch and the CPU. But as I mentioned, the GPU can manage all the data exchange and data flow itself. So what if the CXL multi-headed memory pool or the CXL switch attached memory pool can be connected directly to the GPU cluster? Then anyway, the GPU can access the main memory data just through the CXL switch this is just one hop latency, not two hop latency compared to the existing one. So we can save the latency and power. And CXL basically is a memory agnostic protocol. So according to your workload requirement, you can attach the high bandwidth and the high capacity DDR5, or you can reuse the legacy DDR4 to save the cost, or even memory semantic SSD can be attached behind this CXL switch to increase the capacity or to reduce the cost further. One of the pending question or remaining question is the NDP function, near data processing. Because we remove the powerful computational resource CPU in between the main memory and the GPU. So some kind of the near data function might be required to maintain the performance or to improve the performance. So let's say sharp like the or reduced accelerator can be applied, or the compression and decompression engine for sparsity operation, or the encryption or decryption engine to support the multi-tenant AI training and the other operation, or the data transformer to change the data layout, or to change the file system, and etc. So we believe that there are many the other NDP functions can be useful for this kind of the memory architecture, and we are actively working on this area to improve the performance for this directly attached memory configuration. So I think we are over some time.
Okay.
So
Yeah, thanks. So
that's all we have for today.
Am I coming through? Yeah. Thanks a lot, Tex. Awesome. Thanks a lot, Tex. Next up, we have Isaiah, who's going to present on from Weka IO, going to present next. If anybody has any questions on memory scaling, Tex Sang and myself, we're here all week and always open for conversations and questions. Thank you very much. Thank you.